Dear friends, I'm now going to take up a few problems where you'll understand the context in which we use polar coordinates for the evaluation of a double integral. This may not be an exhaustive set of problems, but we can learn quite a bit. The whole idea about learning so many techniques in multiple integrals is to gain confidence to finally work on problems related to vector integration. So we have already seen that we have used two different techniques of evaluating a double integral, namely the concepts of Rx and Ry, and two, by changing the variables to evaluate the double integral in a new domain. But polar coordinates is another exclusive and a unique procedure to evaluate double integrals. But there's a context. You cannot randomly select a problem and then think of polar coordinates. There is a certain geometry that is involved. My first problem is a very famous problem. It's an improper integral where I have to integrate e power minus x squared dx. The graph of e power minus x squared will be something like this. So this is how it looks like, and you can observe x-axis is an asymptote. This is the point where the curve crosses the y-axis. That's at the point 0, 1. Because for x is equal to 0, e power 0 is 1. So the meaning of this problem, in one sense, is to find the area of this shaded region. This particular problem can be solved in two different ways. One of the procedures is to use special functions. The other procedure is to make a double integral and then evaluate it. Of course, you'll ask, where is a double integral first of all? So what I do is, I'll create a double integral out of this context. So let me designate the integral as I. I can as well make a similar integral using a different variable. It hardly matters whether you use x or y, as long as we are integrating within the same limits and the structure remains the same. Well, now what I do is, I multiply these two to obtain an I square double integral. You can call it dx dy if you want. So now the question is, how do I evaluate this? So for doing this, I use polar coordinates. You know, a point P with Cartesian coordinates x, y can also be given polar coordinates r theta, where there is a pair of transformation equations connecting these two variables that I've already explained in my presentation. The transformation equations are x is equal to r cos theta, y is equal to r sin theta. This looks a very appropriate choice. Squaring and adding these two will make x square plus y square equal to r square. And you can see there's an immediate gain. This part of the function becomes r square. And the Jacobian of the transformation is r, which means dA, which is dx dy, will be Jacobian times dr dt. Please refer to my presentation. These details are there. So now the question is, how does the region look like when you take the double integral into account? X varies from 0 to infinity, y varies also from 0 to infinity, which means that the entire first quadrant of the space of the two-dimensional space is covered by that domain. It's not limited, it actually spreads over the entire first quadrant. We can sort of imagine that boundary, not necessarily a circular boundary, but it could be any boundary. But why not a circular boundary? Because that suits the polar coordinate system. So, because the entire first quadrant is covered, I will imagine my so-called horizon as a big circular arc. So if you look at this region, you can straight away write the variation of r from 0 to infinity and the variation of theta from 0 to pi. This is how theta varies. This is how r varies. So that means it is within these two limits I have to evaluate this double integral. So in the polar system, I square appears like this. So you can see the big gain is x square plus y square becoming r square. And then of course the area element dA will now become Jacobian times dr beta. The beauty about this problem is that this can be easily evaluated. So I'll show this part of the integration here. R is equal to 0 to infinity e power minus r square into r dr. The differential of r square is 2r dr. So I just have to divide and multiply by 2. Half integral 0 to infinity e power minus r square. In fact, we can divide and multiply with minus 2. That makes things much easier. Now, the differential of minus r square is minus 2r dr. So it amounts to just integrating e power minus r square, where all other adjustments are available. So we just have to take this integral and it gives us e power minus r square straight away. So this will be minus half times e raised to minus infinity minus e raised to 0. E raised to minus infinity converges to 0. Of course, e power 0 is 1. Therefore, this output is 1 by 2. I can see that I can paste this result here and then have theta is equal to 0 to pi by 2 half v theta. Now it's extremely simple. The integration of that is theta from 0 to pi by 2. So it is half times pi by 2 or pi by 4. But don't forget, this output is the output for I square. But our original problem is this. So if you want I take the square root of pi by 4. So it is root pi upon 2. Therefore, integral 0 to infinity e power minus x square dx will be square root of pi divided by 2. This is rated as an extremely important integral. It is used even in the theory of probability when we study distributions. So I have taken a integral in the Cartesian frame and then I've created a double integral out of that, then evaluated it. So this is how polar coordinates are exploited in certain cases. My next problem is not so straightforward, but at the end of it, you will understand that it's not, after all, a bad procedure to evaluate certain double integrals. Now, if you look at this problem, I have to evaluate a double integral x square plus y square power 3 by 2 dA. But this language of maths has to be understood. So this describes the region R over which we are double integrating. So it says y greater than 0. That means the region above the x-axis, involving y is equal to x and y is equal to minus x. So those are two straight lines to the origin. And then we want a circular arc x square plus y square is equal to 25 within these bounds. So let us start plotting. So I will start with the circle. First fix your frame and then you draw a circle whose center is at the origin and the radius is 5 units. So mark the 4 important points. The radius is 5 units. Create a circle. But don't start shading the full circle because this circle is truncated by other boundaries. Not the entire circle, but the circle above the x-axis. That's the language of this, so the language conveyed by y greater than 0. Then we've got two very important informations here. Y is equal to x. That is this straight line. So let me immediately label that y is equal to x. And y is equal to minus x would be this line. Let me also label that immediately. So just imagine what the region is. The region above the x-axis between these two lines and the circle, which means it has to be this sector. In fact, if you know the fundamentals of two-dimensional Euclidean geometry, this is nothing but a quadrant of a circle, 1/4 of the total region. Now, if you have to do this problem in the Cartesian frame, it's extremely difficult. Extremely difficult. So, I will convert to polar. So, if you have understood my presentation on polar coordinates, I have emphasized that a region that is bounded by a polar curve like a circle, etc., is very, very convenient to evaluate in polar coordinates. So once again, using the transformation x is equal to r cos theta, y is equal to r sin theta, which automatically takes us to x square plus y square is equal to r square. Then of course dA is r times dr d theta. R is the Jacobian, I don't have to tell you each time. And then comes the region limits in the polar coordinate system. You can easily sense that this angle that the line y is equal to x makes to the x-axis is pi by 4. And this angle, you can measure it like this, or you can also do like this. That is also pi by 4, but with a minus sign. So theta varies from minus pi by 4 to pi by 4. Then we'll have to talk about r limits. Always remember one thing. Any part of a circle, whether it's a full circle or a sector of a circle, which has center at the origin, will have 0 as a lower limit of r. Once again, if you have a circle or a part of a circle whose center is at the origin, then just keep the lower limit of r as 0. The upper limit, of course, will be whatever is the radius of this circle, that happens to be 5 units. Now, this is very, very important for us to transform into the polar coordinates. So, therefore, my double integral in the polar frame will be minus pi by 4 to pi by 4. Those are theta limits. These are r limits. Replace x square plus y square with r square raised to minus 3 by 2 times r dr dt. So, I'll have minus pi by 4 to pi by 4. This should become integral 0 to 5 r raised to minus 3 into r dr dt. So this would become minus pi by 4 to pi by 4, 0 to 5, 1 upon r square dr dt. I would make a small correction to the example. Actually, this double integral does not converge. So what I do is, well, there is also a fault. So I think this minus I can was unnecessarily created. So we'll have a 3 there. Now there is no issue at all. So this would go and simply make it r power 4. No issues with the problem. And the rest is all straightforward. Minus pi by 4 to pi by 4. I integrate this, I get r power 5 by 5, 0 to 5 d theta. Apply limits, I'll get 5 power 5 by 5, that makes it 5 power 4, from minus pi by 4 to pi by 4 of d theta. So this is 5 power 4 times theta, from minus pi by 4 to pi by 4. This is 625 times pi by 4 plus pi by 4. This becomes pi by 2. So I'll get 625 times pi divided by 2. So you can see how very, very easily the computation has become since you move to the polar coordinate system. It is not impossible to do this in the Cartesian frame, but it's not worth it. So this is a problem that I selected because you must understand the range of thetas, the range of r's, and all that. So let us see what our third example is going to be.